first I remind that after this lecture we will have a presentation by Royal about the imaginary project. And I'm pleased to introduce Jorg Schurmann, who will speak about Chern classes and transversality for singular space.
Still on? Yes. Okay, so firstly, thanks to organizers for inviting me to this very nice and perfectly organized conference. It's a great pleasure to be here, and it's my first time to Mexico. I enjoy really the place here, and especially the weather, much better than in Germany, for sure. Next, it's really a great pleasure to present this talk in honor of Pepe. And looking back about what we have done over the last years and thinking about what should be the subject of my talk, I think the only solution was Chern classes or singular spaces. It has to be, in some sense, the subject. Because that is something I think we met around, no, met this later. We came in contact 2001. That I completely remember because it was exactly the year I get interested in the subject. So I think we met sometimes later, maybe at John Paul's birthday conference, maybe, doesn't matter. So it's much later than most of the other authors here, but I'm a little bit younger than most of the other speakers here. So let's see. At that time I was coming from a very different subject. I was working on perverse sheaves, constructive sheaves, stratified Morse theory, and get entrance to the world of characteristic cycles, which you will in the end see in my talk. And I got my own view and entrance to McPherson's order abstraction and Chern classes, and I started to become interested in the subject, and I looked up what people are doing there and which people are working on this, and one should say at the time 2001, characteristic, especially Chern classes or characteristic classes or singular spaces was a very specialized subject. So at that time maybe a small group of 10 people were working on this. Main hot subject was Milner classes. And I think there was a talk last week on Milner classes in this conference. Sorry I missed, I couldn't come earlier. But already it was planned in front of my talk, so it would have been nice. In any case, it's good. And so some of these people are in the audience, not all 10, but of course Adam is here and Jean-Paul left. And there was a team of 3 players, of course, Pepe, Tatsuo, and what was the third one? Jean-Paul, of course. From which papers I learned a lot of subjects, and to see if my view on the things was correct, I tried to look at the papers and to reprove some results, and it turns out most of the time I could do, and sometimes I could do even better. So the way of thinking about was not as bad, and so of course we quickly become in contact from that time on, and you will see during the talk that some interrelationship appears. I'm sorry that we never produced the joint paper, but I think the reason is very simple. We are working on the same subject for this piece. I realized now this week we worked on so many things I didn't know before, but we have very different viewpoint. So, and I think that's very interesting. So we exchange a lot of ideas, we compare the methods, sometimes this method is better, sometimes the other. And this is sometimes you cannot measure in a presentation like yesterday, so I'm not a student, I'm not a co-worker, but still we have a lot of exchange and productful work, I guess. And so I will produce something of this in my talk. After coming to Chern classes, I went at some point quickly, not just to look at Chern classes, but I was more interested in characteristic classes of singular spaces in general. And it turns out there are only very few. So today we pick out the Chern class, but in any case we in joint work with Jean-Paul and another player was Shoji Yokora, which is a good friend and colleague of mine. At the end we could produce an enriched version of this Chern class, which we call motivic Hirzebruch and motivic Chern classes. This will not be the subject of the talk, but I think Jean-Paul was intended to talk on this. In the talk he has to skip thoroughly. So that would be something in spirit what we have seen in the talk of Anatoly. So here this is something like an Betty version. So we work with topological order characteristic and constructive functions. And what we use for the motivic enrichment is motivic Grothendieck groups, and we work with a kind of Hodge realization in the algebraic context. But this is a much more sophisticated subject and the techniques are much more difficult. Still, the results I present are true, in that context also, but I decided to speak just about the Chern class story, which is simpler, and I realized now coming here, I was thinking, all people in the audience knowing Pepe should know about Chern class of singular spaces, because he gives so many lectures, like Jean-Paul, like me. But of course, during these 2 weeks, or the week I realized it's a very different audience here on very different subjects. So I'm happy to choose only the Chern class version, because you should see I will present it also as an introduction to the subject. So I don't assume that you know anything about this. I want to explain the key notions, the key players, some similarities, but have in mind, this is my personal view. This is my approach to the subject, and they are very different views. So Pepe and Jean-Paul have a very different view. Paolo Luffy is working on this subject, he's an algebraic Gemini, has a third different view, and maybe there are many things. So that will be the subject of my talk, and transversality already appears in the talk before, so we will see transversality is also important here. But if you go to singular spaces, there are many transfer notions of these kind of things. Not in the smooth case, they're all the same, but if you go to singular spaces, there are many of them. So since it's in honor of your birthday, a German good tradition is to present a birthday present to you. So here is my birthday present also. I will present you a proof of a conjecture. Unfortunately, it's not your conjecture. It's a conjecture of Alufi Farah from the last 2 years, and you will see in the end. And my proof I have already 14 years ago when I come to this subject, but I never published this. And it proves this conjecture, so you will see. So let's start. So it's my first Beamer talk. I have to get experience with this, but why does it work here? I have to push it somewhere else, or what does it take? You have got 1 week course by Pepe, you got a 1 week course by Jean-Paul on this subject. Now you get a 50-minute talk by me, which is another introduction to the subject. So let's see how it works. Perfectly. Okay, so this will be the result I want to discuss with you. And it's a kind of intersection formula. So the situation is, we work in the complex world. We take singular subspaces in an ambient smooth manifold because we want to do intersection theory. So that is why we need the ambient smooth manifold. And we want to intersect spaces and compare notion of Chern classes. And first look at the second formula. This is a simplified version. So we want to figure out what is the relation between the Chern classes of x and y and of the intersection. And in the end, you will see such a formula comes out. And this is just in the homology of the ambient space. So this is the weaker version. And the thing is, we can, in the end, we can work with 2 versions, which you prefer. You can use this in algebraic geometry context, and the homology you are using are child groups. So here in the end, we work with homology, because the first thing you have to learn, characteristic classes of singular spaces are living in homology, not like characteristic classes of manifolds which live in cohomology. So we are living in homology, and now it depends. I think most people would prefer here the topological view. And then we can even work in analytic geometry. Just take Borel-Moore homology, and people who do not know Borel-Moore homology just take compact spaces. This is the usual homology. But if you're an algebraic geometer like Paolo Luffy, when he formulates his conjecture, of course he's thinking on the world of child groups. Doesn't matter, everything goes through in both versions. So here we take the intersection on the ambient space, and upstairs this is a refined version, a refined intersection, where we remember the support of the spaces. So this is in the end on the homology of x intersected y. So it's a little bit more precise and fine, and if you push it in the ambient space, it is just the usual intersection product you take here. And this is a sort of refined intersection product, which I have written a little bit complicated, because this is the way it will appear all the way in the talk. It's in 2 steps. First you take a cross product, and then you take a pullback by the diagonal. So it's in the spirit of Lefschetz. You take first a product of cycles, and then you pull back, and that is the intersection of cycles. It's a Gaussian map. I will mention on the next slide. The problem is, in the way I state this is not a theorem, but it's a proposal coming up, because there are many choices of Chern classes for singular spaces. I will show you, and maybe it's a surprise for you, there are 7 choices of notion of transversality, and the question is for which combination this theorem is true. You will see for each choice of Chern class there is at least one notion of transversality that it works. And for the Macpherson-Chern class, it works with all notions of transversality. Yeah, so that will be what I want to play. Maybe I skip. So if you go to Chern groups, this is a kind of refined Büsing coming from a regular embedding, so that the space is smooth, means that the diagonal is a regular embedding, and then you can use the language of Fulton's book on Chern groups, but I think most people thinking here topologically, and this is much easier. So what you use is you use Poincare regularity to identify Borel homology with cohomology with support in this subset, and then this Güse magnum homology is just a pullback in cohomology with support under Poincare regularity. So how is otherwise it's difficult to pull back homology classes. So you use your ambient manifolds for getting Poincare regularity. Okay, let me start now to introduce this notion of Chern classes, and maybe I should say it's my first time that I use slides, as most of the authors. It was not too difficult to prepare because the paper was close to finish, so I could copy in, but still, usually I prefer on tables, so if I'm too fast or if I have questions, please ask in between already, and slow me down. We are not in rush. We're going to the end of the story, and you should catch some ideas. So the point is, of course, if you go to singular spaces, it should generalize the notion of Chern classes of a manifold. But since we have to work in homology, we just kept this a fundamental class to map this into homology. And the first Chern class one can introduce is the so-called Fulton Chern class. And of course, I go not to technical details, but I only want to point out what you do is we are working with an embedded context. So we use an extrinsic view on the singular space. That is very different to what Marine and Schwarz has done or something with radial techniques. So we try to find a substitute for the normal boundary. If the X would be smooth, the player would be the normal boundary. So what you can take here is, for example, the normal cone. This is just a cone in general. So think about a C-star invariant subject in a vector bound. So this is the kind of cones we are working here. And for this you can introduce the notion of Segre class, which I will mention later when I need this. I will give you the formula for Segre class. And this guy will depend on the embedding. To get something which is intrinsic to the singular space, you have to correct by the Chern class. So this is the classical Chern class of a vector boundary of the tangent boundary of the ambient space. And I will show you that all Chern classes are of this type. So there are some similarities. Most of the time people say Fulton classes, Macpherson classes are very different. So I want to point out there are a lot of similarities, and I will show you later where the key difference comes in. Another possibility would be what is called the Fulton-Johnson Chern class, and instead of the normal cone, you take what is called the normal sheaf. Yeah? So it's another cone. So there are different choices, but the strategy how to define them is always the same. So you produce to the embedding a cone. From the cone you take a Segre class and you correct by the tangent Chern class of the ambient space. That will be the strategy coming up all the way. And maybe last week you have seen these classes in the talk on Wiener classes, and then the people look at the special case if X is a local complete intersection, then both classes agree and are a little bit simpler, because then these cones are vector boundaries, and for vector boundaries the Segre class is just the inverse Chern class. So then you see here by minus you take a virtual tangent boundary. If you go up to this, this becomes an inverse Chern class. So these Segre classes are a version of inverse Chern classes for cones, which help in this story. Okay, so these notions are very algebraic and Rietvik geometric nature, and you have to be careful. Even in the local complete intersection case, I have this as a boundary. It's not a boundary, a normal boundary in the sense of topology. So there's no tubular neighborhoods here or something. You have to be very careful. It's just an algebraic version of this. And finally, the key players, of course, where our interests now come together is maybe Pepe is on that side, it's the Schwarz class, and I maybe on this side, on the Macpherson class. But luckily we know, of course, we are talking about the same story, which is long ago proved by Brasselet and Schwarz. And so these are different notions of Chern classes for singular complex spaces. I'm working on this side of the story, and I'm of course much inspired by Macpherson's theory. Macpherson's theory is a functorial theory. So you do not speak just about the class of the space, but you plug in a constructible function. Yeah? And of course that is my way of thinking. People who know me, I'm a very functorial person. So don't ask me to calculate anything concretely. Okay, so here now comes McPherson's general transformation. You plug in a constructive function and it ends in homology, and you can use this in analytic or algebraic geometry as you want. And of course, the important thing is, the first lecture we learned Chern classes live in homology, but what should they have to do with the old notion? So before you go to characteristic classes, you should start to think about the degree. Otherwise, it doesn't make sense. And for taking the degree, of course, I need that the spaces are working out compact. And then you look only at the homology classes of degree 0, and you can integrate against them if the space is compact. And what comes out is the Euler characteristic. And if you do this with a constructive function, this is the Euler characteristic divided by this constructive function alpha, a notion appearing in the talk of Luengo implicitly during the week. And this is what I would call Poincare-Off type theorem for singular spaces. Of course, it's not quite true because I do not explain to you what are the indices in this story, because that will not be the subject of the talk for today. And here are different plugs in of constructive function you can choose to get different notions of Chern classes. Function 1 is McPherson classes. If you take the famous Euler abstraction, you get what are called master classes. A Berlin function is very recently that really theory of characteristic classes of singular spaces spread out to application in other subjects. This notion comes up in moduli spaces of threefolds, and the corresponding characteristic class was termed by Berlin the Alofi Chern class. And since in honor of people, maybe I should make a personal remark on Poincare-Off for singular spaces just for you. I think once I met, maybe it was the first time we met at John Paul's conference. You asked me, there are so many different indices of vector fields and one forms, and we unified these characteristic classes. Couldn't I unify these indices? Take me some time, and I find a solution for one forms, because my approach is by cotangent models. And I think I lectured in a conference in Trieste. I gave a very private lecture. So I was a lecturer and 3 students in the audience, Pepe, Jean-Paul and Tatsuo, explaining to them my view of unifying indices. And you see, if you would do this, but that's a different story I will not speak about. If you take this function, this is the Schwarz index, this would be the Euler index, and that would be for hypersurfaces, that would be the GSD index for one forms. Yeah? But that is a complete another talk, and just as a reminder, it was a nice private lecture, I think. Okay, so important here is, so if you plug in different constructive function, and just to mention the end, I mentioned you can do many things. You can plug in intersection cohomology, so I'm coming from constructible sheaf. You can plug in any constructible sheaf, take the stalks of the Euler characteristic, you get some constructive function, and if this sheaf is naturally attached to your space, you get another choice of, this has no name, intersection cohomology Chern class, I don't know, maybe this is misleading. What is important for that, what comes later on, these natural associated constructive functions, so they only depend on the space X, behave nicely under cross product and smooth pullback. And smooth pullback we will use in a moment. So now you have seen there's a lot of different Chern classes for singular spaces. The other notion appearing is the notion of transversality. And now I will present you 2 notions of transversality, and in the end I will present you a third notion of transversality. So maybe this is the easiest you could guess, which is very often used, and we have seen in the talk before. You take stratified transversality. So you stratify your spaces and assume that all strata are transverse in the classical sense. And here for simplicity I take Whitney stratification, so Whitney B, but David will talk in the afternoon about weaker stratification, and it works for weaker stratification. Everything I will talk today works for weaker stratification, so Whitney is just for convenience. So also here there are choices. Yeah? And for example, for the order abstraction, only Whitney A is necessary, surprisingly. Okay, so that is the classical notion if you work with spaces. I want to go to coefficients, but then you do the same. If you have constructible function of this, you take an adapted stratification. Constructible just means constant on strata, and you ask that such things exist. So this is a very simple, naive, but useful notion. And Alofi Farmer, especially Nora Farmer, came up with a different notion, which is much more of algebraic analytic nature. And it's the following. So you ask that at each point you can find local isomorphisms that your manifold splits. into two manifolds, and the spaces are defined in different coordinates. So the first space only the first coordinates and the other one in the other coordinates, which is also a nice notion of transversality for singular spaces. Originally, Eleanor Faber was interested in hypersurfaces, but it perfectly makes sense in any dimension. And so this is clearly of analytic nature, and I extended this definition this year even to constructive function. So you just not ask that you have the splitting, but you ask the splitting is adapted to your constructive function in the sense that the first comes by pullback from the first factor, and the other one comes from the pullback of the other factor. And as a first exercise, to give you an example, if you take this definition, if alpha is locally constant, it is, in this context it's called splayed. Don't ask me what it should mean. It's a notion of Faber, so it's just a different notion of transversality. She called it splayed. I don't know what the meaning of this word really should be. But if you do this for constructive function, as an example, take a locally constant function. And maybe here's the key important point I should point out. Even if you're working in the algebraic world, here you ask local analytic isomorphism. So even if you stay in the algebraic context, the transversality is checked in analytic charts. Yeah? And then you see, for example, that a locally constant function is transversal to any other constructive function, because just take V1 to be a point. Locally constant means on an eyeball, it comes by pulling back from a point, and then it's applied to everything. So you see this notion of splideness for constructive function is not as bad. Here's the remark I've given you. If alpha is locally constant, it's transversal to everything, maybe as it should be. And the other thing is, of course, if you do this for function 1 on a space, the notion of splitement of spaces or constructive function is the same. But if you have it for the spaces, it implies for all these other network choices are presented to you. So the order abstractions are transversal, the Barian function are transversal, the intersection function are transversal. Even more interesting, even the complement, the indicator function of the complements are split, because it's only near the intersection where you have to check something, otherwise one of these functions is locally constant, and then it's transversal to everything. And Eleanor Faber was really, Paolo came up to the subject, they were interested in hypersurfaces and looked at the complement of hypersurfaces working with logarithmic differential forms. That is the origin where this notion comes from. Okay, so let's see where we can start. Okay, and here is now the first result that our general formula works in a suitable combination of notion of Chern classes and transversality. So let's take this algebraic analytic definition of Fulton or Fulton-Johnson class, and then this algebraic notion of transversality is a correct one. It works. Eleanor Faber and Paolo proved this on a paper on the archive in this year, and they have done this for the Fulton class, and I will present you my own proof of this, which even works for the Fulton-Johnson class. And I will give you the sketch of idea, because this idea will return later on in the other story also. It's not difficult. So what you need is, like in Lefschetz construction of intersection, first an exterior product, which never makes problem, and then the pullback. The pullback is the key where the transversality comes in. Okay, so let's see. So if you take a product, normal cones behave multiplicatively, and then sacred classes behave multiplicatively. Surprisingly, this seems not to be in the literature. So I found a proof of this when I come to characteristic classes. I never published this, but this result seems now to become more important, so I should publish it. It's not in Fulton's book, surprisingly. Yeah? And once you go this, then you see the splitedness implies that the normal cone pulls back correctly. Usually you only have the inclusion. I think this one is included in this, I don't forget the key. But splitedness and transversality implies just a pullback, and then sacred classes behave correctly. And if sacred classes behave correctly, you only have to correct by the Chern class of the ambient space to get the Fulton classes, and then the formula is quite easy. So the idea is multiplicativity and a nice behavior under pullback coming from the transversality. That sacred classes behave nicely. That is the key idea I want to propagate. And as a remark, because I switch later to the different viewpoint, normal cones and these Coulomb machines are of tangential nature. You just pull back them. That will be differently if I go to the McPherson story. Okay. Here's another example, and that is the first time we meet Pepe also here. Of course, we would like to meet. Let's go to the most expected notion of transversality. Stratify transversality, then everything is fine for the McPherson Chern classes, even for 2002, and they reproved this in their paper on the archive. Still not published, I think. No? In their paper on Milner classes, and maybe it was mentioned in the talk last week, I wasn't here. For them it's just a byproduct. For me it was also a byproduct. So in this paper I prove a general defect formula. In the case we are here is where the defect is zero, whereas the Milner classes where the defect is not zero is on the opposite end of the results. So we were both more interested on Milner classes, but that is a side step where this works. And maybe this is a good remark now that we have seen. If you go to Chern class of singular spaces, what does it mean? What it measures? Its degree measures the Euler characteristic. So why we need higher Chern classes? So if you look at Poincaré-Roch theorem, you only need degree 0 classes. They see the Euler characteristic. Give an easy example where you need the higher Chern classes. Maybe this is the easiest example. So if you want to calculate, take the degree 0 of this. If you, on this side, if you want to calculate the Euler characteristic of the products, you can't just use the Euler characteristic information itself, you need more. So you need here, you see the higher Chern classes come in. So if you do this, for example, is the ambient space is projective space, the more information the Euler, these Chern classes capture are Euler characteristic of generic transversal hyperplane sections in all dimensions. And with this information, you can recover the Euler characteristic of the intersection. But you cannot recover the Euler characteristic of the intersection just knowing the two Euler characteristics of spaces. So maybe this is a very nice, easy example to show where higher characteristic classes are needed. Okay, and here now comes the conjecture of Alofi Faber. Under this slide, so this result is true under stratified transversality. And they came up with this algebraic notion of transversality, and we have seen the Fulton and Fulton-Johnson class behave nicely, and the conjecture is the McPherson class should be also behave nicely. But the problem is these two notions you cannot compare. They are very different shape. So I will introduce a third notion which is weaker than both of them, but still implies the result. Okay. So now I come to the second part of the talk, and this is an introduction to the, maybe people call the microlocal view on McPherson's story, which is well known since the 80s. And it's a reformulation of McPherson's transformation in the embedded context. Maybe to save time, I put all players on the blackboard. So upstairs, it's almost McPherson's transformation up to some sign. We are working in the cotangent boundary. It's more natural for this story, and then some signs appear. Don't be afraid about the signs, this can all be figured out. And upstairs, this is almost the original definition of McPherson. He introduces the order obstruction isomorphism between cycles and construct function. Surprisingly, he has to invert this, and then applies master classes, and to invert the order obstruction isomorphism is not so easy. In the 80s, a newer proof comes in by microlocal geometry, originating from D-model language. And Claude Savart has another approach to this, and my approach I will show you was through stratified Morse theory to get entrance of this characteristic cycle map. You see, this is the isomorphism needed to go into the opposite order, which is more natural for some things, and we use it today as a black box. So these are cycles generated as conormal spaces to irreducible subsets, so you take the conormal space of the regular part, and then the closures, these are against cones sitting in the cotangent boundary, and what I'm playing here, it's the same like before. I take something conic, I take the sacred class, and correct this to get something intrinsic with the ambient Chern class. So it's like before. So in this sense, these notions are very similar. But now we are working with cotangent spaces. And if I want to map information, cotangent spaces behave differently than tangent spaces. So maybe here just one hint, if you want to see precise definition of characteristic classes, it goes through all the characteristic information coming from stratified Morse theory. I only want to point out the sign has to come in, and this sign here is the reason for all signs appearing in the following formulas. But this is a sign is very important. So that is a correct condition. The other thing is now I can, because I will use it later, give a simple definition of the second class of a cone. Cone means you can projectivize, If you do not want to lose information in the zero section, it's better to take a projective completion. And then you have a tautological line border on this, and you just kept with Chern classes of this to produce what is called the Seade class. So the key step is that we can projectivize the codes. And now we want now to imitate my proof for multiplicativity and pulling back, and now I have to explain pulling back of characteristic cycles. And this is not much covered in the literature. So I have worked out this proof in 2001, my own experience to come to the subject, but I didn't publish. And now, seeing the conjecture of Alofi-Faber, I think I should publish this, and I will do this series because it solves the conjecture which I proved 13 years ago already, but I didn't know the conjecture, it's just recent. So what is the difference? And this picture comes up from Diebold's story, and then the people call this the Japanese diagram in this context. If you go to cotangent spaces, you have a correspondence. You do not have a map, you cannot go from there to there, you have a correspondence. And usually this correspondence is if you go from X to Y. So correspondence means you need one pullback and one push down. The pullback is no problem because we have ambient smooth spaces. So you can use Poincare duality to go from homology to local cohomology, and then you can pull back. The question is to push forward. And if you go from X to Y, this is the functorality of McPherson. This is well known. Then you assume that F is proper, then this map is proper, and then you can pull back, push down, and that describes the push forward of characteristic cycles, and that implies the functorality of McPherson. So it gives my own proof of McPherson's theorem in this embedded context. But this is well known. But what I want to do, I want to do the opposite. I want to pull back. And this is not as well studied in the literature. And then you come to a very natural third notion of transversality, which has its origin in D-mode language, but here you will see it's of very geometric nature. So what I want to do, I start with some cone here, I want to pull back, that's easy, I want to push down, so I need a properness condition. And this is what people call the notion of non-characteristic. So you start with a cone here, and for me, this will be the support of a characteristic cycle, and then this is that it intersects the kernel, so you pull back and it intersects the kernel of this map only the zero section, or what is more important, it's exactly the condition that this map is proper. And then I really have a correspondence I can use, I can pull back and I can push forward. So this is where the last condition is important. But I want to take Seade classes, so I have to projectivize. And if I projectivize this map, I get only a rational map. It's not everywhere defined, but you see this middle condition means if I have this condition, it neglects the space where the projective map is not defined, so I really have a well-defined map for the projectivations. And then it's very easy to control how Seade classes map from here to here. So the Seade class step of cones is then very easy to control. Okay, so now the question is, what is this pullback of characteristic cycles? And the first guess, it should be the pullback of the constructible function. It's almost, but some signs come in. I promised you signs coming in, and be aware, there are some versions of this result in the literature, for example by Ginsberg and Diebold stuff, and they may make mistakes. The sign is missing. There are sign mistakes in the literature. You have to be very careful. So this is the right statement. You will see in the end the proof, and then you will see the reason of the signs. But up to a sign, pullback of the cycles, it's the same as pullback of the function. We learned now that the Seade classes behave correctly, because the projectivation behaves correctly. But Seade classes of the cones are almost the Chern classes. I only have to correct by the Chern classes of the ambient space, and then you came up with a general pullback formula, which in this context is called the Verdier-Riemann-Roch formula. How characteristic classes behave under this sort of transversality, which is now a micro-local notion of non-characteristic with respect to the support of this cone, this characteristic cycle. This works for general maps between manifolds. The case we are interested in embeddings, and in particular in the diagonal embedding. And then you see, so here I write this formula this way because you see this is exactly the Seade class. I mean, we should point out, here we have the sign, here we do not have the sign, because if I correct, I would get the dual Chern classes. If I go to the Chern classes, again the signs come in, and because this pullback is of degree m minus n, it cancels this sign. So if you would do this for dual Chern classes, there would still be the sign. The good news, if you go to the usual Chern classes, the sign cancels out. It will disappear. So the formula looks simpler. Okay, but now we want to go to embeddings, and then it's better to put this factor onto the other side. So M would be a submanifold of N, and then you see what you take. You take the Chern class of the ambient manifold, you kept with the inverse of the Chern class of the submanifold, and this is just the Chern class of the normal boundary. So if you do this formula for the ambient case, it's just putting one factor on the other side, it looks like this, and the correction factor is really the Chern class of the normal boundary. And if you do this now for the case we are interested in, this is a diagonal embedding, because we want to make in Lefschetz type style an intersection. This correction factor appearing in the formula is exactly because Tm is just the normal boundary of the diagonal embedding. And that is where this correction factor from this viewpoint comes up. And so now this theorem proves that this formula goes nicely back. So now I can give you already the proof of the conjecture of Alofi-Fager, even in a more general context, because I can work with constructible functions. The first step was multiplicativity, which makes no problem at all. It works also here. Characteristic cycles behave multiplicatively, for example, the order abstraction. This is equivalent, it's well known, this property. I pointed out that Segrè classes, so again I use this for Segrè classes, behave multiplicatively. Then to correct this, also this is multiplicativity, and you get the multiplicativity of Chern classes. This is well known, this is proved by Krzyzinski and Jokova, but they use resolution of singularities. And this is, from the viewpoint of characteristic cycles, a much simpler, much more natural proof of the multiplicativity. So once we have the multiplicativity, we have the pullback formula. The only thing we need to know is to compare the transversality conditions. So what you see is, we take first the extended product and pullback is just the usual product of constructive function. If you do this on a space level, you take the cross product of x and y and pull it back to get the intersection of x and y. So that is what we want to have in the formula. And now I have to compare the notions of transversality. And the problem was stratified transversality could not be compared with plate, but both imply locally stratified transversal in the analytic sense. So each point you can find a neighborhood, you can find adapted stratification that it would be locally stratified transversal. And this notion is even stronger than the notion I use of this non-characteristic. So the third notion I want to propagate, that should be maybe the outcome of the lecture from today. This is a very natural notion of transversality in the microlocal viewpoint. It is weaker than stratified transversality. It is weaker than this algebraic notion of slightness. Still, it implies the theory we want. Okay, so here comes now the theorem. We assume this non-characteristic condition, and then we get this formula I expect. And the proof was already presented. We have the multiplicativity, we have this pullback formula, and then we get out this formula. And this was the correction factor of the normal one to the diagonal. So this proves in particular the conjecture of Alofi and Faber. As a side remark, we get also from the proof another interesting formula, which I want to use to make again reclam for the microlocal viewpoint. I pointed out that you can't calculate the order characteristic of the intersection of the product from the order characteristic of the pieces. But you can calculate it from the characteristic cycles of the pieces. So assume that the space is compact, then these characteristic cycles intersect in the ambient potential space, in a compact space. Both are of middle dimensions, so the intersection is of degree 0. It's also compact, so you can take the degree. And the degree of this calculates up to a sign. The sign is as before, the reason, calculates the order characteristics of the intersection. So the 0 degree Chern classes do not, but the characteristic cycles make such a formula work. It's just a side remark to the key result. So let's see, I'm good in time. Maybe too fast, I hope not. But, so let's summarize. I wanted to show you different notion of Chern classes, different notion of transversality. I presented all Chern classes as cones, corrected by the second classes of cones, corrected by correction factor. And for the multiplicativity and for the pullback, you need to control the second class behavior. This is very different from McPherson's push forward. And here all these are very similar. Usually people say Fulton classes are not functorial or Fulton, but they look at a different functoriality. For pullback, of course they have some sort of functoriality under a suitable transversality assumption. For them you need this notion of slide, and for McPherson classes also this non-characteristic, the weakest version of transversality is enough. And the key player was of course the pullback formula, so this multiplicativity is the easy part, the pullback formula. And I only claimed that the characteristic cycles pullback corresponds to the pullback of constructive function up to a suitable sign. That was the key result behind this, what I call the... And now let me sketch the idea of proof for this. And that is the last slide of proof of technical things I want to present. So we have this cotangent correspondence, and we start with something here, we pull it back and we push it down. I want to understand this. And this non-characteristic condition you can split off in two cases. Because they behave nicely under composition of correspondences. So the first case you can have to control, which is the easy case, is a submersion case. It's a local statement. If you want, it's even a local statement in analytic geometry. So you can assume that the smooth means it's a projection with a smooth factor. And what you have to understand, you go from the subset to the conormal space, and that corresponds to the constructive function dual order obstruction. It's the order obstruction up to a sign. So the pullback of the order obstruction is just the order obstruction. That's nice, but the pullback of these characteristic cycles is what you expect. This is just a zero section, and you see the sign comes in because under this correspondence to the dual order obstruction these cycles correspond. So you take -1 to the dimension of n, you take -1 to the dimension of n prime, and the difference, here you use only this one, where you start, and in the end you use both. The difference is of course -1 to the dimension of the fiber. And then you see why this sign appears. So here the reason is because you have to go from dual order obstruction to conormal spaces. So that would be the easy case of a submersion. The more interesting case, which is very close also to Milner stuff business, is the embedding case. So the embedding case you can reduce because you do it locally. You can do inductively reduce to codimension 1. And you do it locally in the analytic topology. Okay, so you have the situation where you have a smooth hypersurface, and you start with a typical conormal cone to a reducible subset, and you assume that this inclusion of the hypersurface is microlocal transversal, so non-characteristic in the sense I introduced, even without understanding what it means, but this was a technical condition of transversality. I want to prove that the pullback of this corresponds to the characteristic cycle of the restriction of the constructive function, and the constructive function would be the dual order obstruction of z up to a minus. So the codimension is 1 and minus should appear. So where first comes the minus come from? So there's a general result that this kind of things does not give the restriction to the fibers, but it gives a more sophisticated restriction to the fiber. It gives a nearby. So first, nearby means it's just a picture of Milner fibers we've seen in the talk before. So here I have a function, even a smooth function. So what does it mean on the level of constructive function, these nearby cycles? Take a point here, take a local ball, take the Milner fiber. What this guy then calculates, where is it here, this psi g, it just calculates the order characteristics of the Milner fiber weighted by this constructive function. So this is just the order characteristic version of taking Milner fibers. And this sign has to appear because a generic Milner fiber is transversal to the stratification. So you cut down the dimension of the strata by 1. And I pointed out in the definition of characteristic cycles, -1 to the dimension of the stratum comes in. And here you cut down by a transversal fiber by 1, and that is why this minus sign appears. The other one is a theorem of Savart. Many people have different proofs, but this is a well-known theorem. But still it does not give the wide restriction, it gives the nearby cycles, but we want to restrict. So we need to know that in this situation this is the same, and luckily here's the final statement I can show you, and this is again a result of Pepe. What surprise! Do you remember that you worked in this context? No?
Yeah, of course.
For sure. Okay, so this is a famous paper Lee mentioned also yesterday. So I think, what was it? It was entitled Order Obstruction in Indices of Vector Fields. Maybe published in Topology or something. A nice paper using techniques of vector fields and so on. And this is my response to this. I gave my own proof, trying out to figure out my way of thinking, which is very different. And I came up also to this, and maybe this is my language of phrasing this theory, but using very different techniques and languages. And you see why it's the same condition. In this very special case, that G is a smooth hypersurface, that it should be non-characteristic for this conormal space, just means, if you go through the definition, just means that the differential of G does not kill any limiting tangent space coming from here. And this is exactly the transversality you were using in your paper. So for this hypersurface, in this special case, it is a very particular case of this non-characteristic. So this proves in the end that the Weiss-Polbeck formula, instead of nearby, I can restrict, and that would prove the result. So everything is proved. I'm almost in time. So maybe a last personal remark to Pepe. My response was just a note I put on the archive. It was my first paper on order abstraction. It was a very short paper. I called it a short proof of the paper of Pepe, Jean-Paul, and Chern. And it was short. I don't know, you need 10 or 15 pages. I need only 1 page, but using, of course, sophisticated machinery. I put a little bit subject and text around now, maybe now it's 3 pages, doesn't matter. Jean-Paul at his birthday conference, so the chance for you is also coming, told me he didn't like that I made the proof so short. So he was not so happy about the title, A Short Proof Of. So after the talk you can tell me your opinion about this. Okay, so that was the story I wanted to present it. So thanks to the audience to still follow on almost the last day. And of course, happy birthday to you.
Some questions?
So can you relax a little bit this transversality condition? For instance, if they are transverse away of finite set, and to get some formulas when you have to change your constructible function?
No, of course. If you say it would be transversal up to an exceptional set, this exceptional set would contribute a defect to the Polbeck formula.
Yes.
And that is the same play game as working with Milnor classes, and you have to fix in which situation you are. I have to think about, but it should be that some sort of vanishing cycles should play the role of the correction terms, but I didn't think about, but in principle I think it should be put all my machinery together, it should give results of this type. But here I wanted to present where no defect is, so to show that this non-characteristic condition, which is maybe to geometers is not so well known, it comes from D-model language originally, is still a good notion in this game of a kind of transversality. And about the defects, I would expect yes, but I didn't work out.
Are there other questions?
Yes.
Your method gives the notion of generic hyperplane section for Lefschetz theorem?
What?
In Lefschetz theorem, there is a notion of generic hyperplane
Yes.
section. So it must give something about that.
Yes, of course, you proved this already. So this notion of non-characteristic is this notion that the smooth hypersurface does not vanish on limits of tangent spaces, is a genericity condition. And under this genericity condition, this formula also, this formula is only true, otherwise of course a defect is coming in. This has to do with vanishing cycles as we expected. And I only wanted to point, you have this kind of genericity condition. And in this local case, I want to say that this, for a hypersurface, this non-characteristic is a generic condition. Yes. Or you can do this globally. If you work in a projective space or a homogeneous space where a big group can move your space around, you have a kind of generic transversality statement that if you move with a generic element around, these conditions are fulfilled. Even the stratified one, the strongest, is fulfilled. And I think Faber and Aluffi showed that this is not of this freedom. But this non-characteristic and stratified transversal, if you can move with a group element around, is a generic condition.
As you point out, in this last formula, we are using a generic hyperplane section, and then that's the equivalent of transversality, and what you have is all the way through that formula. Now, when you consider non-generic hyperplane sections, that's what led to our paper with Marcelli, Parameshwaran, and then
Yes.
which you had a similar formula with that effect. I presume that you can also get that one.
I think maybe I'm a little bit younger than you, maybe my reminder is a little bit better than you. I think that was one of the first questions you asked me in the email when you get an email contact or something. And I didn't put this into my paper, but my proof would give it for sure. And that was, but you had written this up, so I didn't need to correct or to extend my paper. That is exactly what you have done in your joint paper. And because I phrase it really to show that some vanishing cycles are not there under this genericity condition, and if the genericity condition is not fulfilled, the vanishing cycles measure the defect. And I think that is a global picture we have. So that is very similar to the picture of Milnor classes. And maybe what one should say out here is now that if you, so Milnor classes and this transversality are on the different ends of the same story in some sense. And my formula I put in 2002 covers both cases.